Okay, what I want to look at is multimeters. Okay, and let's just go into this, make sure that we can get this as it says multimeters. Now, as you can see, there are two types. Digital and analog. Okay. Now, a digital multimeter has a set of digits on the display, and an analog multimeter has a scale with a pointer or needle. You really need both types to cover the number of tests needed for designing and repair work. We will discuss how they work, how to use them, and some of the differences between them. Okay? Let's just give you a good view of these. Okay, you can see some of these you would have seen already yourself in the workshop. Okay, and you would be familiar with the leads and so forth. Okay. Now remember that it is important to have the leads maintained, because a broken lead is no good to you. Now, digital and analog multimeters, or meter, or multi-tester, or even a tester, they are all the same. Using a multimeter, analog and digital multimeters have either a rotary selector switch or push buttons, I should say, to select the appropriate function and range. Some digital multimeter DMMs are auto ranging. They automatically select the correct range of voltage, resistance, or current. When doing a test, however, you need to select the function. I'm just easing back so I can get it into full range. Okay. Now, before making any measurement, you need to know what you are checking. If you are measuring voltage, select the AC range, 10 volts, 50 volts, 250 volts, or 1000 volts, or DC range, 0.5 volts, 2.5, 10 volts, 50 volts, 250, or up to 1000 volts. If you are measuring resistance, select the ohms range, times 1, times 10, times 100, times 1K, times 10K. If you are measuring current, select the appropriate current range, DC milliamps, 0.5 milliamps, 50 milliamps, 500 milliamps. Every multimeter is different. However, the photo below shows a low cost meter with the basic ranges. Okay, and bear in mind also so that you can get very sophisticated meters. The idea here is that the recommended meters for electrical work is the G38, and I believe that that is still the case. Okay. All I'm going to do now is just going on this, okay, so you get a close view of it. Okay, and it's just rotary selector. Now the most important point to remember is this. You must select a voltage or current range that is bigger or higher than the maximum expected value, so the needle does not swing across the scale and hit the end stop. If you are using a Dmm Digital Multimeter, the meter will indicate if the voltage or current is higher than the selected scale. By showing OL, this means overload. If you are measuring resistance such as 1 megohm on the times 10 range, the OL means open loop, and you will need to change the range. Some meters show 1 on the display. Okay. Now I'm just bringing this up a little bit more so we can see it in full range. Okay. So let me just show 1 on the display. When the measurement is higher than the display will indicate, and some flash a set of digits to show over voltage or over current. A 1 indicates the leads should be reversed for a positive reading. If it is an auto-ranging meter, it will automatically produce a reading, otherwise the selector switch must be changed to another range. Okay. And I'll leave it there just so you can see it in full, and you can zoom in at your leisure. Okay. I'm gonna just take a zoom on this. Okay. Now here we're simply showing you where the common terminal is selected. Okay, it's identified, and your range selector in regards to your positive terminal is here. Okay. The common negative lead, I'm going close to that so you can see it. The common negative lead always fits into the common socket. The red lead fits into the red socket for voltage and resistance. Place the red lead, never mind that, whatever, well, red banana plug, they call it banana plug in this case, into A for higher current amps, or milliamps or microamps for low current. Okay. Okay, now just panning out so I can get the main text in. Okay. Now the black test lead plugs into the socket marked with a negative, common or common, and the red test lead plugs into meter socket marked positive or VWMA. The third banana socket measures high current, and the positive red lead plugs into this. You do not move the negative lead at any time. The following two photos show the test leads fitted to a digital meter. The probes and plugs have guards surrounding the probe tips, and also the plugs, so you can measure high voltages without getting near the voltage source. Now they have guards around the voltage tip. This is to prevent your fingers slipping down to the tips and acts to protect you from electric shock. Okay, do not ignore those tips. If they're damaged, they should be replaced. Safety, safety, safety. And again, I'll just zoom in so you can see these in full, okay? And how they're actually connected up, okay? just panning out. Okay. Now, analog meters have an ohms adjustment to allow for the change in voltage of the battery inside the meter as it gets old. Okay. Now all I'm doing here is bringing this close so you can see the readings on the panel itself. Okay, and this here ohms adjust is also called zero set. The sensitivity of this meter is 20,000 ohms per volt on the DC range and 5 kV on the AC range. Before taking a resistance reading each time on any of the ohm scales, you need to zero set the scale by touching the two probes together and adjust up the pot until the needle reads 0. Swing full scale, okay, with 0 swing full scale. If the pointer does not reach full scale, the batteries need replacing. Digital multimeters do not need 0 adjustment. And I'll bring that into line for you, into focus. Okay. Now, measuring voltage. Measuring voltage, okay. Let me just pan out a little bit so we can get it all in, okay. Now, most of the readings taken with a multimeter will be voltage readings. Before taking a reading, you should select the highest range, and if needle does not move up scale to the right, you can select another scale. Always switch to the highest range before probing a circuit, and keep your fingers away from the components being tested. If the meter is digital, set the highest range or use the auto ranging feature by selecting V. The meter will automatically produce a result even if the voltage is AC or DC. Okay. If the meter is not auto ranging, you will have to select V if the voltage is from a DC source, or V AC if the voltage is from an AC source. DC means direct current, of course, and the voltage is coming from a battery or supply where the voltage is steady and not changing. And AC means alternating current, where the voltage is coming from a voltage that is rising and falling. And that will be your sinusoidal waveform for those of you who does not recall it. You can measure the voltage at different points in a circuit by connecting the black probe to chassis. This is the 0 volts reference, and is commonly called chassis or earth or ground or 0 volts. The red lead is called the measuring lead or measuring probe, and it can measure voltages at any point in a circuit. Sometimes there are test points on a circuit, and these are wires or loops designed to hold the tip of the red probe, or a red probe fitted with a mini clip. You can also measure voltages across a component. In other words, the reading is taken in parallel with the component. It may be the voltage across a transistor, resistor, capacitor, diode, or etc. In most cases, this voltage will be less than the supply voltage. Now, if you are measuring the voltage in a circuit that has a high impedance, the reading will be inaccurate up to 90%. If you use a cheap analog meter, okay. And again, as I've said, the recommended meter is G38 for electrical engineers. Now, is that G38 or GS38? Just check and make sure that it's correct before you do anything further. I'm just trying to establish if there's been any changes to that from which I became familiar. But okay, we'll see how it goes. But check and check and check. Okay, safety, safety, safety. Now here I've given you an example. All I've said here is that here's a simple case. The circuit below consists of two 1 megohm resistors in series. The voltage at the midpoint will be 5 volts when nothing is connected to the midpoint. But if we use a cheap analog multimeter set to 10 volts, the resistance of the meter will be about 100 kilo ohms. If the meter has a sensitivity of 10K, and the reading will be incorrect. Here how it works. Every meter has a sensitivity. The sensitivity of the meter is the sensitivity of the movement and is the amount of current required to deflect the needle full scale. This current is very small, normally 1/10 of a milliamp, and corresponds to a sensitivity of 10K kilo ohms per volt, or 1/30th for milliamps, for a sensitivity of 30K per volt. If an analog meter is set to 10 volts, the internal resistance of the meter will be 100 kilo ohms for a 10K volts per meter. For a 10 kilovolts movement. If this multimeter is used to test the following circuit, the reading will be inaccurate. The reading should be 5 volts as shown in diagram A, but the analog multimeter has an internal resistance of 100 kilo ohms and it creates a circuit shown in C. Now you will need to come back to this yourself again so that you can see what I'm talking about as I move forward. The top 1 megohm and 100K from the meter creates a combined parallel resistance of 90K. This forms a series circuit with the lower 1 megohms, and meter will read less than 1 volt. If we measure the voltage across the lower 1 meg, the 100K meter will form a value of resistance with the lower 1 meg, and it will read less than 1 volt. If the multimeter is 30K ohms per volt, the reading will be 2 volts. See how easy it is to get a totally inaccurate reading. Now you will need to read this for yourself, and you will need to recap on what I've just said, looking back at the text in itself in your own form. And this is what we're talking about, okay? And this is how we would look at the measurements. So here we have a, well, parallel network here. So you will need to calculate that total resistance of these two resistors, which will then become a single resistor link in series with this 1 megohms. Okay. So what we're looking at here is the changes, how the circuit can change simply by misreading of information. Let me just go back a little bit and let me just move in. Okay. Okay, let me move out a bit now. Okay. Right, I'm going to stop there for now because this is quite an extensive information piece. And I will try and pick this up again at another point in time, but I will upload this and again do some additional work for yourself, do some research, look at how the resistance can be calculated, okay, and I will try and pick this up again from due course. Okay, now for me, let me just make a record for myself. This is page 6. I'm not going to tell you how many pages there is, but this is page 6 for me at this point in time. Okay. All right, have a good day. Thank you. Bye-bye.